So just let me, so I know kind of what to talk about. Anybody here heard about Parallella before? Okay, all right. So I don't. So I have to. So for half of you, it'll be new. For the other half, maybe it'll fill in some of the gaps or some of the backstory. Now, what about application areas? Who here works on hardware or systems and software? Science. Okay. All right. Cool. Now this. By the way, so anybody who wants to get a hold of me in regards to collaboration or something like this, you can always reach me at andreas@adaptiva.com. I receive a lot of emails, but if it's interesting, I always respond. I've worked in chips since 1996. I graduated from University of Pennsylvania and went to work for Texas Instruments, and then I worked for Analog Devices for 10 years after that, designing DSPs. So in 2008, I decided that I was kind of wanted to try on my own. I started my own company. But I also had this very, very deep belief that whatever we were doing at Analog Devices was wrong. Whatever people were doing at Intel was wrong. You know, there was just, you know, having designed the execution units and the buses and things like that inside the chip, you realize the waste is incredible. I mean, it's unimaginable, right? If you take a billion transistor chip, right, you might have 10 million transistors doing useful work, right? That's, I mean, it's amazing how, and when I say useful work, I mean the math part. To me, you know, the floating point unit is what does the work. Everything here is just there to support the floating point unit if you're doing mathematical processing. So, you know, having seen what we did on the, I designed a chip called the TigerShark DSP. The floating point unit there was less than 3% of the total chip area. And of course, power is directly related to the chip area. So I figured, hey, if do a good job, we can cut out 97% or close to that. So that was my goal. Of course, you know, we're so used to Moore's law that we don't always realize how big 25x is, right? Because we've seen a million x improvement over 20 years due to Moore's law. And so people are used to just seeing 25x every few years. Let's look at another industry, car industry, right? 25x would be like going from Patagonia to Alaska on one tank of gas. That's not going to happen, right? That's, and yet we think that the chip guys will get us another 25x in a few years and another 25x after that. And I'm telling you, it's all going to stop, right? It's, you know, silicon scaling is going to end in a few years. We already seen performance scaling is stopping. So 25x is a big goal. Now, you know, why did I do this, right? Why not trust, you know, Analog Devices, Texas Instruments, and Intel? Obviously, they have a very good track record for 30 years, designing better processors every year, every 2 years. You know, why go out and compete with them in something new? And so this is a graph from Intel, you know, surprisingly enough, that shows, you know, kind of, okay, so the green curve here, right? This is Moore's law in effect, right? You put more transistors on the chip every year, and you get this exponential improvement year over year. So that's all great, right? We can still produce more transistors, and we're still on that curve. It's going to end 2018, 2020, but for now we're doing great. Now, clock frequency, 2002, 2004, flat line, right? It used to be 1 megahertz, 10, 100, 1,000, 2000, 3, 4, and then at 4, it was just getting too hot. There was just no way you could cool the chips. So that stopped. And that's related also to this curve, the power, right? The power, same thing. Drawing 100 watts out of a 1 square centimeter area is very, very difficult, right? This is, you know, thermal physics. So you start saying, all right, there's no way you can get it out of it just airflow. So you put a heat sink on it. Now the heat sink heats up, so you still need a lot of airflow. And then you might start with liquid cooling, right? But at the end of the day, it's just too dense and it's too hot. So that kind of stopped, right? So they said Intel doesn't really make chips above 130 watts anymore. That's, you know, it's just not going to happen. And then the last trick that they had was, instead of ramping up clock frequency, let's do dynamic scheduling, right? Let's have hyperscheduling. They found that the programs really couldn't make use of it. The compilers couldn't make use of it. So So this is the trend, right? You see these 3 plateaus in the last 10 years, and performance really isn't improving very much. Of course, what they did then was when they went dual core up there, and then quad core, and then 8 core. And then you start saying, all right, well, that's working pretty well. Now you look at the supercomputing guys, which have been doing SMP, massively parallel for 20 years now. And what they're finding is, right, peak performance actually goes up pretty well, right? It's because when you think about it, all you have to put out are more servers, right? You can make a Google-type data center with millions and millions of servers and scale out to infinity, right? Network, well, you can make pretty good networks today. And the peak power requirements are just going to scale with that, right? So if you put 1 server, you have 20 kilowatts or 10 kilowatts. You put 2 cabinets. You put 2 cabinets, you have 2x that, and so forth and so forth. But what they were finding was that the efficiency gap, right? The achievable performance by programmers compared to the peak theoretical datasheet number was growing. So now you're still burning the power because everything's always active, but you're not achieving that with your program. So now the efficiency is even worse. And so that's a big problem. And of course, that's the easy problem. The hard problem are these 2. So if you take anything battery operated, anything like a smartphone or an iPad or anything like this, a sensor embedded system, you're going to be driven by your battery, right? How long can it last? And that has been growing very, very slowly. So whereas Moore's law is kind of like double transistors every 36 months or something like this, the battery density was barely moving. So you see this gap. And I think we've seen that in the last few years, right? It used to be that our Nokia phones lasted a week on standby, a few days on talk time. Today, we've been, Pavlov trained to charge our phone every day, right? As soon as we hear that beep, low on battery, we just go look for an outlet, right? My phone doesn't last a day. So you can see the problem, right? And so, and what the ARM and the SoC guys are doing, they're basically following the same trajectory that the desktop guys followed in the 90s. What do? They ramped up clock rate. Now they're making the cores more advanced. So they did the ILP one, they did the frequency. Now they're doing multi-core. And then every time you go, all right, now what? What are you going to do next? And so there's all kinds of problems with the current way of doing things. So then the question becomes, so who cares, right? Maybe we don't need performance. And there's some truth to that, in that a lot of applications don't actually need more performance. So in the desktop processor, I think most people today, unless you're doing heavy-duty gaming or scientific processing, you can pretty much buy any old laptop or any old desktop and it will work. Used to be that you bought the latest stuff to have your stuff run faster. Today, it doesn't really matter. Now the smartphone couldn't really run any kind of program. Today, an application processor inside your Samsung phone or Apple can easily run Ubuntu, the latest 14.04 Ubuntu with good performance. And so you figure, all right, so anybody doing regular email browsing is all set. That whole application space, CPU is an uninteresting problem. But the problem or the challenge is there are still areas where I think there's a lot of interest for more performance. And sometimes it's more performance, and sometimes it's more performance for a certain amount of energy, so longer lasting battery life. And these are the 4 areas, right? Now, so in 2012, when we did this Kickstarter project, we got a lot of customers from all over the world, business, hackers, and everything. So these are the 4 areas where we got the most interest and that there's the most really excitement for. So one is communication. So the idea is that every single person on Earth should have always on communication. Right? There should not be a place on Earth where you don't have access to data and voice. Now, in order to enable that, you need really, really dense cells. So lots of small cells in urban areas, solar powered in rural, and so forth. So that all comes back to very, very energy efficient processing. So it's ops per picojoule that people care about. Internet of Things, same thing. If you want to have a sensor out there in trillions of sensors out in the world, they should really run forever. So solar powered, or they should run a battery that lasts for years that you can then just throw away the sensor. Buy a new sensor every 3 years, but it lasts there for 3 years. So you can imagine just kind of a rain cloud of sensors sprinkled out there somewhere. So that same thing, if they're disposable sensors, right? So you can throw them away. And the third one is robotics. So either landlocked robotics, right? So on the ground, or drones. So in both of those places, it's very much weight limited. So a very smart robot, right? I mean, I'm talking about human level, not human level intelligence, but fairly advanced intelligence. The kind of Siri, right, of robotics that can make autonomous decisions. Today, you know, the IBM Watson, for example, that famous IBM computer that won't beat a human on Jeopardy, that's a couple of racks, at least, of computing. Now here, we're talking about something that should fit into a shoebox, if it's going to be practical. That needs enormous amount of compute density. Same thing with drones. A drone today, a small one, has a payload of 100 grams. 100 grams, you can fit a small battery and a small board, pretty much. And then finally, you know, the kind of warehouse, super scaled data centers and supercomputers. Today, the leading supercomputer in China draws 25 megawatts of power. And there's programs today in China and the US to build an exascale computer, so 10 to the 18th flops at the current rate, right? So the Chinese supercomputer, number one, which runs all on Intel-based stuff, they run 24 megawatts, 33 petaflops. So they're about 1 gigaflop per watt. So if they just scale up from here to 1 exaflop, you can pretty much multiply, 24 megawatts times 33. So we're up around 1 gigawatt for one computer. That's crazy. That's absolutely insane. So somebody should do something about this. And there, 25x makes a big difference, right? Instead of a 1 gigawatt computer, you have a 50 megawatt computer, which is still very large, but at least it's not 1 gigawatt. And the cost of running such a computer, I mean, in the US at least, it's about $1 million per megawatt. So you're talking about $1 billion to operate the computer every single year. So my kind of my revelation, which came to me in a very specific moment. I know it can be a marketing term, this epiphany, but to me at least it was a very specific time where I remember, okay, now I know everything fell into place. So the idea here is that we're going to throw away everything, all the legacy, but still learn from all the history of computing. At least that was what I wanted to do. And so the idea is, all right, so it should be C programmable, because, or some high-level programmable, but I chose C because C has been around for decades. Everybody understands it. There are millions of good programmers in C today, so I said it's going to be C programmable, so no new language. And so if you state that it's going to be C programmable, you need truly ANSI C programmable. You need a regular processor, so a RISC processor. And the challenge was, how do you make, if everybody has a processor, how are you going to get 25x? So it turns out that if you strip away everything and start from scratch, no legacy, you can get to 25x. And the keys are, don't put in caches. Caches is one of the biggest memory hogs, so there's hardware caching. Don't make a very big instruction set. So instead of having hundreds of instructions like you would have in a CISC or a very large RISC machine, you have 25 to 35 instructions. Don't put in an MMU or memory protection. So basically, don't design this for a operating system, right? This shouldn't run Linux or something like this. This should be tuned for a specific purpose. And the specific purpose is math crunching. So that's the idea, right? So start from scratch, say it's going to be C programmable, but code will be designed from scratch. Now, once you make a very small processor, of course, you can put thousands of them on a single chip. And then the question becomes, how are you going to connect them? You can connect them with buses or with some kind of crossbar. To me, at least, the only one that's been truly proven over decades has been mesh networks. It scales fairly well. It's super easy to design. And so I designed a 2D mesh network. And in terms of the memory system, like I said, it's no caches. Caches are bad for many reasons. One is energy consumption. The other one is scalability. So once you have thousands of cores, where are those cores going to get the golden copy from DRAM? So every time you have a cache miss, you're going to go out to DRAM and fetch something. Well, what if you have thousands of processors having cache misses? You get a huge mess in the memory system. And then you start looking at things like cache coherency. So how do you keep everything coherent? So you have all kinds of bottlenecks that prop up. And if you say there is no hardware cache, there's local memory, but everything has to be managed by the application or by the runtime, then you can actually have it scale much better. So, and then, kind of the glue logic that fits, all the multi-core communication, DMAs, also had to go in there. But so the claim when I started this was we can achieve 25 times better than Intel, which I truly believed, right? Based on my back of the envelope calculations, it should be possible, but it seemed kind of crazy at the time. So in terms of the architecture, what is it, right? It's a 32-bit architecture for now. It's C99 and CC programmable. It's a dual issue, so it's similar to like an ARM A9, which today is in every smartphone in the world pretty much. It has a lot of registers, so 64 registers, unified between floating point and integer, which is great for unrolling loops. It's very easy with a C compiler. IEEE floating point for math, but for so this is very simple, right? This is something that you would find in Hennessy and Patterson with the MIPS architecture. Didn't take me very long to design the first version. Certainly an undergrad or graduate student could also design something like this. But I think the key innovation here or important conclusions here was what we threw out. It has to be heterogeneous computing, right? It has to be a specialized machine that's a little bit special but not too special. If it's too special, nobody will want to touch it, nobody will want to program it. If it's not special at all, well, then you're just reinventing the same thing that exists today. So kind of walking that fine line between in specialization. So the mesh network is a 2D mesh that connects all the cores in the system, right? And how it works is you take the upper 12 bits of the address space, that gets routed around the network, and at every node there's a comparison between that coordinate, the 12 bits, and the node's address. And so you do an XY routing, right? You go along a row and then you go to the column. And it kind of hops along like that. So if I get from, if we are go back here, right? If I want to go from here to here, I have an address generated by my C program inside here. If it's a local address, meaning it starts from address 0 up to 1 megabyte, it's basically like a telephone number without an area code, then it doesn't go out in the network. If it's a complete address with an upper 12-bit set, then it goes out of the network, and then at every node there's a question asked, what's the row, what's the column of this destination, what's my row, what's my column, and does a comparison. And then in this case, if I want to write to 3, 3, well, if the network's, what it does is passes the transaction along, hops. Here it's going to be a column match, and it's going to send it down. Once it gets down to here, it's going to say there's a column and row match. Let me send it inside the core, and it's completed. So that's how the routing scheme works. So there's no routing tables to manage here, right? Everything is managed on a per transaction basis by the network. And one of the cool things here was all the network on chip work that had been done to date when I started this was assuming that you had kind of a macro network that was boiled down to a chip. So you had things like wormhole routing, virtual routing, buffers and tokens and things like this. And usually where you had a packet, a header and a payload. But of course that's done in macro networks because wires are very expensive. So when you connect a cluster together, you have lots of these things running around, right? It's you find out that if you're not careful, you're mostly wiring and very little compute. Well, on a chip, wires are free. Wires is you have 9 layers of metal, and basically wires are the things that pass over your transistors, right? So you have 1 layer of transistors, 9 layers of metals. You pretty much never run out of wiring, and so the idea here was let's pass buses, buses in parallel. So instead of having a packet header and a packet payload, just pass the whole packet on every clock cycle. So you waste some wires. You may even waste the destination address on every transaction, but the trade-off is simplicity. So Whereas, for example, what we do here, we pass 104 bits on every clock cycle. 32 of those are address. So you waste 32 bits of address on every clock cycle, where you could potentially do a streaming thing. But on the other hand, you say, well, if I didn't have that, then I would have to have all kinds of mechanisms in place not to deadlock and to keep quality of service. And you say, right, which one costs more? And here with simplicity was the choice. And I'm pretty sure, given our data, that that was the right choice. And in terms of the mechanism, there's also a lossless pushback throughout this network. So you can basically keep pushing out transactions, and then if the traffic ever backs up, it backs up at the same speed that you can push through. So it's kind of like brake lights on a highway. You're never going to crash into anybody. So this is me in 2011. 2011 was a very good year. So the chip, this is Epiphany 3. Epiphany 1 was a prototype that I basically designed out of my basement, but it was a 65 nanometer chip with 40 million transistors. It worked, but barely, right? But it worked well enough to get some investment, to bring 2 friends along. So now we're 3 of us. So we designed Epiphany 2, which would have been a product if it wouldn't have been for a bug in one of our IP providers that made the floating point unit not work. So again, not really our fault, but I think it was still good that they paid us to do Epiphany 3 then. Epiphany 3 worked perfectly, and Epiphany 3 is the one that is now shipped on all the parallel boards 3 years later. So this was good. 3 months after this, we taped out a 28 nanometer design. So we'd just gotten the 16 core back in 65 nanometer. And we did this work in less than 12 weeks at 28 nanometers. So 64 cores, 100 gigaflops. And this is also same parallel board, different chip. And this was a prototype. So to do a production chip, you need to pay the foundry about $3 million to do that. And this was just a prototype, kind of small volume run. So you pay a few $100,000 for that. But we paid a few $100,000, got a 28 nanometer chip done out the door. We announced it. And so we're basically showing that we can do 100 gigaflops with 2 watts, which is 50 gigaflops per watt. And today, the best kind of computers in the world the best chips in the world will do 10 maybe. The best computers in the world will do 1. So the 50 gigaflops per watt number was a big deal. And I thought once we release this, we'll either be bought or big customer will come along, it'll be great. All our problems are solved. We did our part, now they can do their. And so just from some perspective, again, what this means. This is showing 28 nanometer silicon areas for different cores from big companies like Intel, AMD, ARM, and then our Epiphany chip at the bottom. And you see that we're anywhere from 4x to 100x smaller in silicon size compared to our competitors. But the reception we got was brutal, right? It was so disappointing, right? That to find out that here we've worked 24/7 for 3 years. In my case, put every single dollar I had saved up for retirement and everything else into this company, and there was nothing, right? It was done. Nobody cared. And I think we could have been 1,000 times more efficient than Intel. Nobody would have cared because we did not have the software. And we had the C compiler, we had the debugger, we had Eclipse, we had a story, but nobody wanted to leave their programming environment that we're used to with the whole software stack pretty much done and take on something that was a blank canvas and they had to draw everything from scratch. In retrospect, we should have known, but I'm always an optimist, so I always believe that you build it and then somebody will see it and have faith in it and take the chance. But that never happens, at least not what I've seen. Of course, we're not the first people to try this. I thought we've done it differently enough to these companies that we might have a chance because we were C programmable, because we had floating point, where most people didn't. But it turns out that the failure rate for parallel processors is perfect, right? The success rate is 0%. zero. Yeah, even some great companies, right? Inmos, right? You can say that they had lots of tractions, lots of researchers, but did not have the staying power to become a general name and sell. To me, staying power means that you get into systems that are sold all over the world in volume, and you're around for 20 years. That is staying power. But one thing with Inmos and the transputer was they came so early, right? So 80s and 90s, Moore's law was in full effect. Intel was coming out every 18 months. There was no way to keep up, right? So these kinds of parallel accelerators, when Moore's law is in effect, you can't keep up the cadence. You release one chip, and then by the time you get that to market, Intel's already had their next chip, and the next one, and the next one. You just can't keep up. Of course, today is different. Today, Moore's law is slowing down, and now the accelerators and the parallel processors have a real chance. So, but the recent ones, Palestra, for example, is a parallel processor company in Boston. They were just sold for very little to a network processor company. So that's the end of the road for them, but they did a really good job for 10 years, came out of MIT. So they kind of paved the, Inmos and Palestra completely paved the way for us. So when we go into places, usually we can use those as reference to say, well, have you heard of the transputer, or have you heard of Palestra, right? And if they have, they're usually our friends. They like what we do. If they haven't, then we're in for a long road. An interesting company now is XMOS. So it's a British company founded by David May. Of course, David May also founded Inmos. Was the architect of the transputer. So I think there's an interesting connection here. Of course, now the second time around, he started this XMOS company, and initially it was a lot about parallel programming and the parallel programming model, and it was transputer 2.0. Now they've kind of changed their direction a little bit. They're going after more application stuff, automotive, audio, and they're using the parallel processing as a tool to create solutions. I think it's a very good direction, and they're doing quite well. They just raised a lot of money from Bosch, from Huawei, and from Xilinx. But what I would like to see is a parallel processor architecture that's completely general purpose, where the programming is not done by the company. It's done by the people, the users, the community, and that has never happened before. The only thing that's come close has been GPUs, right, with CUDA and OpenCL, where actual programmers and scientists are writing code and sharing it. Now you have a network effect, and you're building upon that. To me, that's the model. So of course, once we had the C compiler and GDB and some libraries, people wanted much, much more. They wanted a programming model, kind of like we have today for single-threaded processors, like whether it's Python or Java or even C. And then we started looking at parallel programming models, and since a small company, 5 people, we could basically afford to make one bet, right? We can't say, oh, we're going to do everything. We're going to, because it would cost many, many, many millions of dollars. And so we looked at all these things, and we tried to pick, right? Criteria was how many users do they have? Are they open source? Does it make sense? Does it fit our architecture? Is there industry momentum? And so a lot of these things fell out immediately, right? For example, CUDA, right, is very popular. It runs on NVIDIA. It's completely proprietary, which makes it completely uninteresting, to me at least. And I think it should be uninteresting to a lot of people. Things that are open, right, now they put that in a different group. And then the question was, does it fit our program model, and does it have momentum? So we go here, Erlang, a language invented by guys at Ericsson 20 years ago, seemed at the surface great, right? It's built for robustness, for scaling, but it's a very non-traditional language. But the runtime there is quite large to enable this kind of fault-tolerant computing. We can't put that kind of runtime on our very, very small and simple cores. So for now, that's been out. But Haskell is kind of in the same class. Haskell is interesting, but usually because it has a fairly complicated runtime, hard to fit it there. So we kind of, new architecture, we need to think of a micro runtime that still keeps the kind of functional programming of Erlang and Haskell. OpenCL generated a lot of attention. It's kind of like CUDA. Industry consortium, open, so yes, that's great. We did an OpenCL compiler. That was our one bet initially. Spent a lot of money on that. Then it turns out that we started running code, and we found, okay, no problem. We can run almost any type of code out of the box, but performance stinks. Because this dirty secret of OpenCL, it's not like C programming where you can push a compiler and get good performance on Intel, ARM, MIPS. OpenCL is completely dependent on the type of architecture you have underneath. So if you're programming in OpenCL for a GPU, it's different from a multi-core, it's different from our Epiphany. You need to write your code specifically for a hardware target, and it can be quite substantial, we found out. So that was disappointing. Now we're working on OpenMP. I think that's a better programming model for us. OpenCL is a little more tuned towards GPUs and massive number of threads and massive data parallelism. OpenMP is more modest threading. So OpenMP we run with, like you basically do a fork join, 16 threads. So I think, and easier to use, right? The number of lines of code, here you might put in a pragma, here you're filling your programs with tens or hundreds of lines of code. MPI comes from the supercomputing in space, scales very well, but again, not the easiest one to use. It's a single program, multiple data. You need to start thinking about making identical programs with control statements, if else, that ask questions like, if I'm thread 0, I'm going to do this. If I'm thread 1, I'm going to do this. And so you force a thought process on the users. But that's kind of an idea of a lot of parallel programming languages and which one we kind of focused in on. So, problem, parallel programming is hard. Right now, I would say it's very hard compared to single-threaded programming. I mean, let's make a standard, right? Let's say you're writing a Python script, right, that does something that's not performance critical. You could bang that out in 5 minutes, right? Now, a hugely complex parallel program. And the other thing is, you wouldn't even do a program in parallel unless it was complex. Because if it's easy, just write your code and run on a single-threaded processor. So you know you have a performance problem. So you have to get it correct and you have to run it fast. Otherwise, there's no point in running it in parallel. So you have these multi-factors here. And add to that, right, debugging, right? You have non-deterministic behavior if you have multiple independent threads running. The tools are kind of immature for parallel programming. So, and of course, productivity matters. You just want to get the job done. You need to make money, right? So if you spend 1 year designing a program, right? Let's say a US salary is $100,000, right? Where are you going to make the $100,000 back from? If you're writing an app or something. So, it's a huge deal. And very few people even know or are educated about what parallel programming is. So, but the big lesson here that we learned was nobody wants to go backwards. Nobody wants to go back to assembly programming. Punch cards. People want to move forward. So they always want to be more productive than they were the week before. They want it easier, not harder. And you come in with a parallel architecture, you tell people, nope, this library doesn't exist, you're going to have to write your own. Nope, you don't have your regular Eclipse IDE, you're going to have to do something different. So huge hurdle. And an understandable one at that. So now here, so we designed chips, right, 28 nanometer, and we spent a lot of money on that. But there's no way that a 5-person startup was going to solve this problem, right? There's been billions of dollars spent on this in research, government grants, and trying to solve this problem, right? I mean, if you just look at these languages alone, there's way over $1 billion invested in designing all of these languages and all these paradigms. So we're not going to do it, right? There's no way. We don't scale like that. But we can collaborate, right? So if we do open source collaboration, maybe we can be the vehicle that can enable all these other people to innovate. That was the idea. So in 2012, after the company basically was done, completely failed at getting market penetration, we would have gone out of business if they wouldn't have done this. So we launched this crowdfunding campaign on Kickstarter. So Kickstarter is it's a platform where basically the creators of projects, hardware or others, artistic, you put out an idea and you ask people to put in money, and they usually get something in return. They always get something in return. Like in our case, they got a board in return as a reward. but it's not a store, right? Because you explain that you haven't designed the product yet, you want to design the product, and there's some risk, and would people be willing to pledge money for the chance of getting this unique product? So that's what we launched. So we launched this thing at $99, which is pretty crazy considering that the list price for the zinc FPGA that was on this was at the time $120. This was definitely the time when my own optimism got the better of me, and it truly got me in trouble, because I figure at $99 we're going to sell 1 million of these, and there's going to be so much momentum, kind of like the Raspberry Pi, that Xilinx is basically going to give away these chips for free, just for the chance of being part of this, right? I mean, it wasn't quite like the volume price for this chip was $18, so my fallback was 18, but they didn't really say what volume meant. So I figured somewhere between $3 and $18 for that chip and everything else on it, we can get to 99 and break even. But I assumed on all the chip pricing, I assumed we would get volume pricing for all the chips, because if you don't, it's usually about a 4x factor between volume and chip number one that you buy from a company. But of course, if we only sell 5,000, that's not volume. None of the chip companies care about 5,000 units. They're going to say, you're going to pay full price. And so if I hadn't convinced all these companies that had chips on this board to give us volume pricing, the board would have cost us $400. So this was scary, but we got there eventually. But so the idea here, what's on this board? It's an open source board, which means that all the layout, all the schematics, all the components, the BOM, everything's available. It runs only open source software, so no binary blobs. All the drivers are there, Linux, Ubuntu. And then in terms of hardware, it's got a dual core RMA9, so it can run Ubuntu quite well. It has an FPGA on it. Now I'll get into exactly why we chose that, but it's kind of a nice bonus for this board, even though it wasn't the initial goal. And then gigabyte of RAM and Gigi interface, HDMI. So you can actually use this as a complete computer, right? And the model here was Raspberry Pi. And then we have 16 or 64 core Epiphany coprocessor. So initially we set 2 goals for this campaign. We said if we raise $750,000, we'll produce a 16-core board for $99. If we raise $3 million, then we can actually produce a 64-core board, because at that time we'd gotten the chips back, they worked perfectly, but we didn't have mass production masks done, and that costs $3 million. And finally, 50 gigabits of I/O, so which is quite substantial, and is another one of those kind of thought-provoking benefits of the board. That, all right, if you had 50 gigabits per I/O on a credit card, what could you do with that? What kind of sensor could you interface it to? So that's the board. This is the board zoomed in. So again, credit card size, form factor, connectors on each side. And one of the ideas here was we didn't want to create an eval kit for our chip, right? I mean, chip companies do that all the time, and usually every 12 months they come up with a new eval kit for the new chip, and then you have to abandon your old work and get a new one, and it's very disruptive. We wanted to make this an open source platform that's around for many years, so that educators, researchers, people can use this in systems that look like real products. And so we put the connectors on both sides, right? So kind of like a back panel, front panel on a device. So you can imagine this sitting in a box, kind of like this, right? So yeah, HDMI, USB, gigabit Ethernet, UART, kind of serial protocol, and 5 volts in. This runs down to 3.7 volts, so you can actually run this off a regular LiPo battery, like one of those thin ones you'll see in a smartphone. And you wouldn't have USB if you did that, but you could actually run the processor and everything else using that. Then we have the Zinc, this dual-core ARM FPGA, and the Epiphany processor. On the back side, we chose to use these robust Samtec connectors, they're called. We chose that because of the pitch. So whereas most boards today will have if they're hacker boards, they'll have a 0.1 inch pitch headers, right? So low frequency, right? No high frequency stuff, not dense connectors, but they're very easy to hack, very easy to interface to. And so I went back and forth. I looked at the board called the BeagleBone, looked at the Arduino. I felt, no, this is wrong, right? This is not our market. We need to go after as much bandwidth as possible, as small as possible. And then, you know, for that, Samtec was a pretty good connector. So the idea here is that you use and symmetry, right? So we could also pick one connector for power, another for I/O. We thought, you know what, same height, very uniform is an advantage. So power control, so things like JTAG, ASC, UART, basically anything that we couldn't afford to fit here, or anything that not every person needed. So we only put things on the main board that everybody would need. And the idea is that anything else you put with the daughter card, so expandability. And so we have this power control, so you bring out all the power rails, 8 rails on that, and then you have these other connectors for I/O. And the first connector is basically 48 signals that you can hook up into the FPGA that you can make do anything. Any interface, camera interface, LCD, other sensors, IR, motor control, you name it. I mean, this is your canvas, right? So design a board with something on it, you hook it up to the FPGA. I mean, I love FPGAs, right? It really is the blank canvas. And then you have these two guys, right, which connect the Epiphany chips or the boards here to other boards. And so one of the unique properties in this architecture, just like the transputer did back in the days, was that while we have, let's say, up to 64 cores on a single chip, you can actually tile the chips together on a bigger board to infinity. So make these enormous mesh networks that connect to each other. And so the idea here is that we couldn't quite get all the 4 links out. So in this case, the Epiphany has a north, east, west, and south. So the east connector is connected to the Zinc. That's the co-processor interface. And north and south would be connected if you had, you know, multiple boards in kind of a ring or a linear array. So, you know, for those of you who don't know the parallel, the idea here is that when you boot up the board with the 5 volts, the Zinc here is going to go out to the flash memory and flash and bring in a bootloader called U-boot. Once you have U-boot in, then he goes out to the SD card and looks for a Linux kernel or any kind of OS, any kind of program really, and it starts running that. And then, of course, after that, now you have an OS, you know, you have DRAM and everything else, the kernel's loaded, you're all set. It loads in the drivers. Same thing, the file system by default sits on the SD card, but you could just as well load a file system with U-boot from the Gigi connection. Once you're up and running with the ARM, running Linux, the way you interface with the Epiphany is just as memory mapped I/O. You can read to the Epiphany, read from the Epiphany, write to the Epiphany. You can load programs. So the API, if you imagine now that you're sitting in a you know, writing a C program running on the ARM, you write your regular C program, and now you hit a bottleneck where you want to speed up. So now you use 3 function calls. You do load program, you do read and write, and the loaded program is something that is a Epiphany program you wrote, a C kernel or something like this, that you compiled with the Epiphany C tools, GCC. And it's now sitting in your Ubuntu file system or Linux file system. You load that L file into your program and say, run. So that's kind of the system model for the parallel. In terms of the goal of this project, right? Besides saving the company, that was certainly a pretty important goal. But just as much, it was really actually trying to make some good, right? So everybody recognized that making parallel programming easy is a big challenge that everybody needs to solve. Otherwise, we won't have any more performance to gain. Serial performance is completely flattening out. So we need to learn how to do parallel programming. We need to teach it. We need to make the tools better. We need to build up the software stack from scratch. And what the goal here was, we are going to make an open source platform that's going to be that vehicle. And so we had some principles. One, complete and open documentation, right? So and no NDAs, right? So basically, all the documentation should be up on the web, and people should be able to go download it. And this is completely opposite. If you look at these companies out here, very few to almost none of them ever disclosed their specs on the web. It was always, very secret, very proprietary. You get access if you signed an NDA. And the mistake I made was I looked at all these companies and said, oh yeah, that's what you do, right? You have to protect yourself. You have to be paranoid. As Andy Grove would say at Intel, only the paranoid survive. Well, it works for Intel, doesn't work for a startup, because as a processor company, if you don't disclose your stuff, you will never have anybody write any software for you, which means you're going to die of starvation. So this was a great thing, right? In realizing that, it's actually less risky to disclose the documentation than it is to not disclose it. And what we found was that once we disclosed everything, the spec and the data sheets, a lot of the fear, uncertainty, and doubt went away. Whereas before it was, oh, these guys, this is vaporware, it doesn't exist. And then people looked at the spec and said, okay, we're still doubtful. We still doubt that it exists, but at least it makes sense. We like what we're seeing. Not everybody, of course. Some people thought it was a terrible idea, but we got more people that liked it than didn't. Low cost. So we used to sell our kits for about $10,000. And that, again, was the standard, because that's what all the other parallel processor companies had done. Between $10,000 and $50,000 per kit, with proprietary software, and a big box usually that they shipped. And we found that, yes, we did win some of these contracts, US government contracts, where they would pay us $10,000 for a board this big with some software that we packaged up. And but we, again, so few of them that was no way to scale it. And then, being inspired by Raspberry Pi, if you build something cheap enough, then all of a sudden everybody can afford to buy it. We could never make this for $25. I wish we could, but we could make it for $99. So we brought the access point down, the cost. And open source software, open standards, and free choice, right? So that's a big thing. We're not trying to push the programming model on the user. We say now that, and we didn't want to pick the programming model out of those 30 or so parallel programming models. We're just going to focus on making a canvas that people can draw upon. Open source hardware. So we decided that so that people could innovate, they can actually access all of these hardware files, design their own boards, produce their own boards anywhere in the world. And I would say that a lot of these things actually have already paid back, right? We've actually seen very little damage. We haven't seen any clones. Why would there be clones when we're so small, right? So the idea of the paranoia, right? You only have that problem if you're hugely successful, right? We could all wish to have those problems. We haven't seen any issues with things like that. What we have seen is that by open sourcing, we got people to give us expertise. They would review our schematics. So we built a board, right? Looked like this, and then we realized that it was, well, we didn't realize, we knew it was going to draw 5 watts. And 5 watts for a credit card size board is above the threshold of what you can do comfortably. So if you look at something like Raspberry Pi, which draws 2.5 watts, 3 watts, or even less than that now with the new version, that's no problem. The way I kind of look at it is, it's a little bit like a bathtub, right? Where you have water coming into the bathtub and water draining out. If you're slightly above the ratio, eventually it will overflow, right? Even if you just delta above, wait long enough, you'll overflow. And so what we found with this board was that, 5 watts, the board can't dissipate 5 watts without a heatsink. So initially we put a small heatsink on the zinc, and then it was still running too hot. And by too hot, you mean, all right, it might work for a day or 2 days, but eventually it's going to die because it's running at 95 degrees C. So we put a bigger heatsink. Now it's better. But the lesson here is that you You have to be very careful about the size of your solution and how much power it's dissipating. The smaller you make them, the bigger the problem. It's the Intel problem again with the processor, right? 130 watt out of a centimeter type square die is impossible, but even 5 watts out of a credit card is challenging. And so one of the things that, and so the solution that we had was, well, people can just buy a little fan. That was not a popular decision. It was a bad decision because we didn't anticipate the psychology and the users that we had. So whereas I'm a hardware designer, I can put up with pretty much anything, right? I mean, hardware is a lot of work for very little reward a lot of times. Software is more fun, right? You know, you can move faster, you can innovate more quickly. So we should have designed a box and a fan around it. If we would have said, we're going to ship this thing with a box and a fan, even if there was a fan inside, nobody would have cared. Plug in the cables, put in the SD card, you're all set. But because we shipped a bare board and we asked people to solve their own thermal solution with a fan, you can imagine kind of like, all right, now where do I find a fan, right? We'll go up on the web, search it, and things like this. This was a big problem. So we put up all of our sources on GitHub and opened up a forum with thousands of users, because the idea here is that a 5-person team doesn't scale. The investment doesn't scale, right? Whereas Intel is a $50 billion company. They put between $5 to $10 billion in R&D investment, product development every single year. Here we're a 5-person startup that is consuming, less than $1 million a year, right, in terms of R&D. So $1 million versus $5 billion. So the only way to do that is through collaboration. So we have to set up a good framework for collaboration. So just some perspective, right? And part of this is Moore's law, but it's also hardware economics and it's new parallel architecture. So the CM5 was also a parallel architecture. It wasn't as dense, because you didn't have as many transistors back then, so you had different economics. But the number one supercomputer in the world in 1993 was the connection machine, CM5. Beautiful machine with 1,000 processors, asking price something like $30 million. Mostly the customers were like the NSA and DARPA, number one. If we compare this to the 64-core parallel, the one I'm holding in my hand, 66 processors, 100 gigaflops at 5 watts. And if we would have raised the $3 million, we would have sold this for $199. And so it's kind of fun to think when, like 20 years later, you truly do have a supercomputer in your hand. Not a supercomputer based on the Chinese standards today, which is 24 megawatts and 33 petaflops, but a 1993 supercomputer. So whatever program you could run in 1993, right? I mean, these were nuclear missiles, these were weather simulations, these were molecular dynamics. Today, within an approximation, you can kind of run those things on a credit card, which is mind-blowing, right? So how do we take some of the stuff that people worked on for 20 years and transfer them to the embedded domain? This is going to be fun. So we designed some kind of system examples just for our own sake. Of course, our goal is really for other people to design this. One of the things we did was we want to make easier access, so we designed a breakout board. That way people can start hacking around. This one right now we give away to anybody who asks for it, who has an interesting project. Soon enough, we're going to release this probably next few weeks into a distributor's hands, and then anybody who wants to can buy one. And basically what we did is, brought out all these connectors, so you can get about 130 signals or so up here, along with a PMOD connector and JTAG, and this one, this is another very, very disappointing moment where we put together a cluster with 2,000 CPU cores, basically 32 of these 64-core, 66-core cards, completely conduction cooled with the networking, right? So the switches sit down here, power supply, and 32 boards. drawing about 200 watts. And so we got this to work, showed a demo at International Supercomputing Conference, and it was like nothing, absolutely nothing. There was no interest. And then we looked around at the conference and we realized none of the other accelerator companies had any interest either. NVIDIA was trying, but not a lot of interest. AMD, nowhere to be seen. It was all Intel. It was all Intel all the time. That was the only thing that mattered. And so instead of Intel has de facto monopoly, right? Like 90% plus market share. They weren't shrinking their market share. They were growing their market share at 90%. It was absolutely amazing. So all the people walking around, they were not interested in looking at new hardware. And so just kind of shows you how much momentum the legacy way of doing things, how much they have, right, with the stack. So instead of people looking at parallel architecture, they're looking at adding more layers of abstraction on top of the hardware. So today in the data set, for example, it's all VMware. It's all virtual machines. So whereas Intel and again, this is just my view of the world, but whereas Intel and Windows would have a pretty nice collaboration on the desktop, and that made both companies very, very rich. In the data center now, VMware and Intel are killing it and making a lot of money together. So VMware doesn't run on ARM, it only runs on Intel. So anybody interested in running VMware, Intel. They also have designed some very good chips that support the features needed for virtualization. But the momentum industry is virtualization and big processors with as many users on each processor as possible, not thousands of cores. So this, again, it's a nice prototype system, shows what you can do, but certainly we have a long way to go. But that's fine, it's just more data. But we have had some success. So now I know we're going to be okay because we have big customers who are buying into it. Not your average customer, but people who are willing to write their own code have invested serious time and money in using the architecture. So one of them is Ericsson, the communication company out of Sweden. They show that Epiphany, the 64-core version, beats Intel Xeon by 25x in their benchmark. So the whole thesis from the beginning has now been proven by somebody else, and they even published an open white paper on the subject. So this is which you can download from our webpage. I thought that this was really nice. This was validation, and they invested quite a lot of money in the companies after they showed this. There was another government customer, same thing. They ran a long evaluation, and the criteria was they wanted to run the same code, the same kind of bit shuffling kernel, which they would never tell us what it was, C code, unmodified, that they ran on Intel on a coprocessor. So they said they don't want to run CUDA because CUDA is a different language. They want to run pure C code, ANSI, C, C99 code. And they also showed 25x. Then there was an open source group out of Russia where a master's student ran a password cracking algorithm called bcrypt and published it at Usenix. And they also showed 25x. So 3 different independent groups have shown that with C code you can reach 25x. And now the question is, well, who cares about 25x? And that's the next kind of big question. One thing, right? My favorite physicist, Richard Feynman, right? He used to have a famous lecture in the 60s that says, with all the advances that have been made in transistors and shrinking them, there's so much room at the bottom, right? We don't stop until we can manipulate atoms, right? Or maybe we can go farther than that. But the idea is that we're very impressed by Moore's law, and we get more and more performance, smaller. We can always do much better. So the example I want to show is this is a TNT2, the most powerful computer in the world today. So 33 petaflops, 24 megawatts, $400 million. It's not even the most expensive supercomputer in the world. That's the K supercomputer from Japan, which cost $1 billion to develop, and which is slightly less than this, but is a much more advanced architecture. They designed their own ASICs, for example, based on Spark, whereas this is just put together based on Intel products. But this is just crazy. I mean, this is not the way to do things. And so just to show you the scale, right, between a room full of stuff, and this is just showing the data center, the cooling and the air conditioning and the power delivery for this thing is definitely twice as big as this, sitting somewhere in another room. I mean, these people are just posing here, right? I mean, that's but the amazing thing is right. If you were to take 28 nanometer wafers, if you look at the amount of processing power on 16 of those wafers, right? The size of them would be the size of this frisbee right here. The size of that frisbee contains as much processing power as this whole room. Of course, if you were to turn on all those wafers at the same time, running at 1 gigahertz, you would consume a lot of power, right? You would consume on the order of 1 megawatt. Now you can't draw 1 megawatt of thermal power out of a frisbee, right? That's too much. But I think it's a very thought-provoking exercise to consider that in terms of performance, it's there, it's latent, right? You go from this to this. I mean, that's many thousands of orders of magnitude in terms of density. So now what, right? So we launched this board in 2012. It was extremely difficult to achieve because of the goals that we set. We said it's going to be cheap, it's going to be 99 because that's what we promised people. We didn't want to move from the credit card size form factor. We couldn't back off on performance either because that's what we promised. So we kind of painted ourselves in the corner, and there were lots of financial struggles with that, but thanks to Ericsson and other investors, things eventually came together. But so this year, we're doing much better. So we had some production issues with some of the vendors on the board as well, which were kind of weird. But everybody in the end delivered. So we've shipped now 10,000 boards, 6,300 of those to Kickstarter. Everything else has been orders or distribution. So now we're shipping on a continuous basis. We have distributors, Ars Components and DigiKey. We have now over 200 university collaborators. 100 of those have gotten free hardware. So we basically made an agreement that says for every 100 boards we ship, we give away a free board. So we've donated about $10,000 in hardware to universities all over the world, and it's been great. It's been a lot of fun, and we also learned a lot from these universities. So what they're working on, where the interest level is, and a lot of people looking at parallel computing now, computer science, parallel programming models, education. Robotics and drones is definitely our sweet spot in terms of the usage model and what people can do with it. This is where we need embedded supercomputing, is in robotics and drones. Software-defined radio is a very practical type of application, and the idea here is that for decades, U.S. government researchers and others have said, wouldn't it be cool if we had one device that could be the universal radio? Put an antenna on it, wide bandwidth that can transmit from DC to 6 gigahertz. And then we have some high bandwidth converters, right? So you can move a 30 megahertz or 50 megahertz band anywhere in that ratio, sample it, do everything digital, DSP, right? That's been the dream. And the government, U.S. government has spent billions of dollars in that area, many billions of dollars, have achieved nothing, right? They had a famous program called Jitters, where the idea was to make this kind of software defined networking stack for mesh networking for little pocket radios that every military guy would have. In the end, again, spent billions of dollars, built something that was subpar. Today, because technology has caught up, it's possible. You can put a radio front end from DC to 6 gigahertz into a parallel card, and you have a universal radio. So satellite communication, emergency radio, digital broadcast, as well as GSM, LTE, and 5G, so Wi-Fi as well. So that's pretty cool. And then finally we have HPC. So to me, HPC is the last one we're going to go after, because we've been there for 6 years. programmers in HPC depend on a lot of software to be productive, a fairly tall stack. So there may be niche applications there, but it's not. They can always, add another power plant. They can always put it next to the Columbia River. Whereas a robot, if it's going to weigh 1,000 pounds, is not really that interesting. So I think commercially, this is the one we're going to focus on. In terms of infrastructure, we're going to keep working with hundreds of universities. Anybody who wants to work with us, we'll work with them, and that's what we're doing right now. So these are the universities right now that work with South America. I don't see USP on the list. So, but I think it's pretty broad, and a lot of exciting programs. And going forward, we're gonna. Obviously, with 200 universities working on it, we're starting to see master's theses and some publications come up. But there's a pipeline, right? So it's usually people get aboard within 1 year they publish something. So by next summer, I expect to see tens, if not hundreds, of publications around parallel and use cases. And one of our goals is kind of survive until the harvest comes in. So just some general lessons from the parallel project. One was the huge value of openness if you're selling a product. So for us, a lot of the people we found were actually willing to pay more for an open product, because then you can hack it, they feel more safe with it. And this may be a little bit counterintuitive, right? So openness may expose you to clones. On the other hand, you can charge more for it. And even as a customer, we learned this, right? So we right now we're doing active research in drones. And we bought this kit from a company called 3D Robotics. They have a forum called Do It Yourself Drones. And so they sell this drone for $750. And it's a very good drone. But we bought it because it was open. There's no other really open platform that people that you can basically buy off the shelf. And we could have bought a proprietary one for maybe $300 or $400. So we decided to pay $750 to get an open, high-quality platform. And secondly, we built a system in New Hampshire, in the U.S., for $99. Whereas the common wisdom would be, you have to build in China. There's no way to build in the U.S. But we made it happen, and we made it happen together with our partner. So the lesson here was, don't believe the stereotypes. If there's an effort, you can do pretty much anything. But you have to play within the rules. So for example, in the US, the labor there for workers starts at $15 to $20. So you have to make sure you cut down on labor as much as possible, versus maybe in China where labor cost might be $2 to $5, right? So you can afford to spend more time on labor. So your design decisions even could make a difference. For example, here there's some through holes, right, on our board. So through holes, if you have the machine, you can make it automatic. Anything that required manual labor, now you're paying a lot of money. Testing, need manual testing, adds up very quickly. So you have to know your cost constraints. Collaboration continues to be a huge investment, in that you can't just throw it over the wall and say, I built it and then I wrote the specs or something like that and everybody's going to take care of it. Sometimes maybe if you're really lucky, somebody will come along, but we found that they're getting people engaged and working with them is, for every 100 that we meet, we find one person that wants to really work with us, right? Because again, we're not hiring them, we're collaborating. They're either being paid by somebody else for doing that work, which is the best case, or they are doing it for fun, which is amazing. Finally, time, right? So when we launched this kit, and we thought that people would go out and buy their own cables and buy the fan and stuff, we should have known that everybody today is super busy, and that you have to make it as easy as possible for people to turn it on. And so going forward, our goal is really to sell a kit. Everything is in the box. you unbox it, you plug it in, and you boot your computer. Because otherwise you end up losing half the people. They get the board, they put it in their drawer, so they paid the money, they haven't used it, it's bad for them, but it's really all bad for us, because without users, the software ecosystem is never going to take off. And this is ease of use, right? At the end of the day, one of the main reason why CUDA from NVIDIA is so popular, even though it's proprietary and people are upset with it, it's easier to use than something like OpenCL. And ease of use is going to win over performance almost any day. So just another little pitch on open source. So we have benefited in a huge way from open source, both as recipients of people contributing to us, but as consumers, right? We've taken stuff. And in the middle, we've given back, right? So everything we've done, we've open sourced. But we've used Linux that Xilinx and ADI created, a port from the kernel. U-Boot, the bootloader, same thing from Linux and ADI. Ubuntu from the Linaro organization, the ARM consortium that takes care of ARM porting. BeagleBone, so they had a Creative Commons open source board that I learned a lot from, because this was my first board, so a lot of the little tricks learned from that board. Verilator is a GPL source Verilog simulator that we use to design the chips. So whereas a proprietary license from Synopsys or Cadence might cost $10,000 each, here we got an infinite number of licenses that were actually running faster than Synopsys to design our chip. It was created by Digital initially. And then once we open sourced our tools and the board, these are some of the contributions, and it's quite significant that people have made. Eclipse multi-core, Tylera spent over $1 million developing that. We worked with Ericsson with their open source tool to get a lot of contribution there. Published some of these results already. OpenCL, we had to pay some money to get this done, but we chose a company that has an OpenCL GPL licensed compiler, whereas all the other companies, AMD, NVIDIA, Intel, ARM, everybody has a closed source compiler, right? So everybody wrote their own, which is pretty crazy when you think about it. When GCC, right, everybody decided, you know what, it doesn't make any sense for every company to make their own compiler. It just takes away the profitability for all the companies. Let's pool our resources. Together we can make a compiler, reduce the engineering overhead, and we can all make more money. OpenCL, they went back to the old primitive ways. Oh, everybody's going to write their own secret sauce compiler, and that's how we're going to differentiate. So every company ends up spending $5 to $10 million in developing an OpenCL compiler. We're not going to do that. This guy in Maryland, David Ritchie, wrote an OpenCL compiler that runs on NVIDIA, AMD, Intel, and us. And all we had to do was add Delta to his compiler, or he had to add Delta to his compiler to make it work for us. This is one of the university projects. We didn't have a multi-core functional simulator. A student at Chalmers University in Sweden wrote a multi-core simulator by looking at our GDB and binutils code. Really, really bright guy. So bright, in fact, that I hired him 2 weeks ago. So this is the kind of collaboration that was great. And finally, our Kickstarter backers, some of the really enthusiastic ones, contributed open source project to our GitHub repository. So we set up an examples directory and said we really need contributions from the community to show like other people what you can do with it. And these two guys in Japan did a Mandelbrot demo, a ray tracing demo, a Kinect demo, and what happens after they release those examples, it kind of has this networking effect that one person uses an example, so he doesn't have to recreate that work, and then he adds his part. So the guy who did the Mandelbrot example probably worked a few weeks on it, uploaded it, then a guy who's a well-known ray tracing guy in Japan took his code. Within 24 hours, he'd done a ray tracing real-time demo on the parallel board. Obviously, it fit really well. He didn't have to do a lot of work. He basically took his ANSI code, recompiled it, and multi-threaded it. And it was kind of the embarrassingly parallel problem as well. But it was truly impressive. So these are kind of the ancillary positive things that have come out of the parallel board that we haven't really paid for. So what we're looking for in terms of parallel programming, and I think the whole programming community needs these things, right? So one, the explorers, right? So you have the guys who are going to make parallel programming easier, because there's only so many people who have a high threshold for pain that want to do parallel programming the way it's done today. The second one is really, really important, the mathematicians and the algorithm guys, to write algorithms that scale. So today, there's been, used to be algorithms were written, image processing algorithms, to minimize the number of cycles. That was the only thing that mattered, right? People looked at assembly instructions and clock cycles, and then it became, GPU time, right, from 2009 to now. And then everybody started looking at, all right, how do we make SIMD parallel algorithms, right? Vectorized algorithms. How do we make a search that can run vectorized? Because the fabric underneath was SIMD. It was a vectorized engine. Now, we're asking people, can you write algorithms that are massively parallel, threaded, and that scale in terms of performance? So not vectorized, working on one bit of an array at a time, but massively threaded on kernels. That's interesting. And then finally, you have to create the whole stack. So let's assume we have a language, compilers, debuggers, and IDEs, and all this stuff. Now you need libraries, because nobody wants to write an FFT or a linear solver, right? Or something like this. So if anybody who works at the science level, needs all those things done for him, right? Like the GNU Scientific Library, for example, right? Or MATLAB. If people can work in MATLAB, they're very productive. If they have to write an FFT algorithm and the code for that to get their stuff to work, most people say, no, I'm not doing that. People need to publish. People need to get their work done, right? They can't afford to spend, and writing a multi-core parallel FFT is not easy. It's not trivial. It's a piece of work. So getting that whole stack rewritten is going to cost somebody tens of millions of dollars, I reckon. And so there has to be a collaborative project. And then finally, if you look at the teaching, right? So today, at least in the US, a lot of the programming in might be Java or Python or something like this, where you teaching single-threaded type of recipes or constructs or methods. Well, where is the parallel programming course? If every piece of hardware is going to be parallel going forward and heterogeneous, it needs to be fed into the curriculum. The hardware is already there today, but if there are no programmers, we won't really see people making good use of the existing hardware. So this is what I've learned from first 15 years of chip design, and then at this company, kind of what are the constraints going forward, and in terms of hardware, very, very hardware centric. So performance limits, that's the Intel graph in the beginning, right? The frequency and everything else. The only answer seems to be massive parallelism. How else could we get 1,000,000 time performance if we start today? We could only scale out to 1,000,000 times, right? We can't get 1,000,000 times from frequency. Thermal density. So we struggle with this. Everybody struggle with this. When we go from 28 nanometer and down to like 14 and 10 nanometer, it's only going to get worse, right? You put more current in a smaller area, which means things are going to heat up more, which means that you have to run them slower. So not even 1 gigahertz. You have to go down to like 100 megahertz. So they spread out the heat, right? So lower clock rate means less dynamic power, but then you need more cores. But the idea is you don't want to make it too dense, right? Just dense enough. And things will fail. So you have bit errors, soft bit errors, right? From cosmic particles crashing in. You have issues with yield, right? It's very hard to make a 100 billion transistor chip perfect. You could make it perfect, but nobody could probably afford to pay for that chip because it would cost $10,000. And the foundry needed to produce that perfect 100 billion transistor chip might cost $100 billion to build. So the idea here is, what if we can make chips that fail? We don't want to make them perfect. They're imperfect. So they might have bit errors here and there. They might have susceptibility to noise or something like this because we want to run them at a low voltage rail to save power. What effect is that going to have on hardware? What effect is it going to have on software, right? So if your software will fail, assume that your thread will fail when it runs. How can you overcome that? Bandwidth. So when we make things smaller and smaller, today all the I/O comes out from the size of the chips. So if your area grows as L squared and your I/O grows as 4L, the bigger you make your chip, the bigger the I/O problem. Density, right? So when Moore's law stops, where are we going to get our density from? And fortunately, we haven't even gotten started yet because we haven't built 3D yet. Nobody's really building 3D at massive scale. The sensor companies are, the SoC companies with package-on-package kind of are, but the really exciting stuff is going to happen when you start sandwiching 10 dies, one on top of the other, and you make use of now your I/O can be L squared again instead of 4L. So nobody today is making use of this kind of area I/O for memory bandwidth or for chip-to-chip interconnect. And that's another dimension that we haven't used yet. So that's going to be a step function once the manufacturing gets done. So that's actually good news. So in the next 5 years, we are going to see I would say 10 to 25x boost just from that in terms of bandwidth. Efficiency, right? So if we do want the productivity, right? Because Python and Java is so easy, but we want the efficiency of like an Epiphany or a GPU, really the only way you can achieve that is split the work, right? So keep everything non-critical on the CPU. You have 1 or 2 cores that burns a few hundred milliwatts, and then you put all the heavy crunching, which is 10% of your code somewhere else. That way you really only have to rewrite 10% of your code. So if you have 1 million lines of code, you write 100,000 lines again, or maybe even less. So these two go hand in hand, right? So the multiple languages, multiple pieces of hardware. Andreas' law that comes back to the scalable multi-threading, right? So the thousands of threads, new mathematical algorithms with no dependency. So the supercomputing guys learned this, decades ago. If you really want things to scale, you can have 0 components that are in your system that are dependent on the data size. It's okay to have a fixed setup cost once, but then after that, everything has to be can be no AMDAL bottlenecks. Development cost. So just like we found with Linux, nobody really could compete with Microsoft on a heads-on, because what happens, or Intel for that matter, what happens is anytime somebody gets a lead in a market, they make more revenue, which means they can spend more on R&D, which means they're going to increase their lead if they have good engineers. And then they just run away from the competition every single time. This is kind of a universal market observation. But what Linux showed was that if everybody pulls together and pools the resources and open sources things, then even the big proprietary companies that have monopolies have no chance. They will lose eventually. That's latency, I forgot to fix that. Never mind. So what I would say is, considering the hardware exists today already, somebody should start rewriting all critical code to be scalable to at least 1,000 threads. There needs to be runtime systems or specific code that manages memory in software. So there's no more cache. So who's going to take care of getting data in and out of a chip? That has to be done by somewhere. So right now it's manual by the application. There should be a runtime that takes care of that. And the other thing is, very few people think about where their bits are stored in the system. If you have a data center, or if you have a motherboard in your laptop, do you know where your DRAM is in that board physically in relation to the processor? And so very few people think about that, but at least in this architecture, the memory here, the 1 gigabyte of DRAM, is actually to the east, right? Is to the left of the chip, physically, but also in the memory space. And so you have actual physical locality, and the further away a bit is stored, the more energy it's going to take to retrieve that bit For example, in this case, you have to go through the FPGA logic, through the memory controller in. And if this was another board, you have to go through the Ethernet and out on the cable and come back. So distance really matters. In terms of the hardware, right? If like Erlang and Ericsson, you assume that hardware will fail, and it will fail a lot, or like what Google does with MapReduce, you just say, things will fail. How can I possibly write my program assuming that things will fail all the time and still have it work? And of course, most software we run today is not going to be able to handle that. You have, if anybody has a flaky software and doesn't have ECC turned on, just wait how long it takes until your computer crashes. And of course, I mean, I'm sure most people already do this today because of productivity. You need lots of languages, right? I mean, absolutely minimum of 2, but it could be 3, 4, or 10 languages to get the job done. Not just so there's no homogeneous programming where you just kind of check into your C++ environment and never leave that. No, you're going to be doing C or C++ or maybe even something like Erlang or MPI to get the job done. Future, heterogeneous, right? So CPU is going to be there maybe for another 100 years, because if you're doing email or word processing, why use anything else? There will be accelerators because the CPUs just cannot keep up in terms of energy efficiency. We've already proven that there's a 25x improvement in terms of just raw density. So where I would draw the line is anything up to 100 gigaflops is easy for a processor. There's no point in going anywhere else. Anything above that starts to get very hard. And I don't see how a CPU will ever really get above 100 gigahertz. Because in order to do that, either they have to create massive vectors per processors, which makes it useless for most applications, or they have to bring up the frequency, which is definitely not going to happen. So 100 gigaflops is kind of the limit. FPGAs, because it is still very expensive design chips, millions of dollars, FPGAs is this kind of thing where you get a fabric and pretty much do anything with it. And so it's a very, very useful tool. And I believe it's going to be around. And then finally, when you have an algorithm locked down, let's say, for example, we have an optical flow algorithm that we've tuned for years in software, right? So we've gone through hundreds of iterations in software. Now we think we have the math down to the most efficient it can possibly be. We can always put that into an ASIC. And that's going to give us about 100x on top of that if we do it right. And clearly, possibly 1,000 times over these two. So this is my final slide. So this shows what, first of all, what we built already, right? We built and improved in silicon, and other people have used it, so it's not vaporware, it exists. If we were a bigger company, this would have been a product that shipped in volume. But 64 cores, 32 kilobytes per core, 100 gigaflops at 2 watts. 2 watts peak, 0.1 watts idle. So this was done in 2013. This is a fact. Now we're working on a new chip. So double precision floating point, more memory per core, and that's going to be out somewhere in 2015. And so those are pretty benign, right? Say 64 cores. Now the key here is the how do we scale to these bigger numbers? So our chip sizes today is about 3 by 3 millimeters, so 10 square millimeters. Now if you look at the GPUs or the FPGAs, the big ones are 500 square millimeters. So we're about a factor of 50 smaller than those chips, which means that you can always scale up. If you want to consume more power, build more expensive chips, you can scale up today at 28. So we can easily go from 64 to 3,000 cores today. That's just build a bigger chip, engineering. Now, going to 2018, right? So now we go down to 10 nanometer, maybe even 7 nanometer, do some aggressive circuit techniques, which we haven't done yet, and you do 3D stacking. So 3D stacking of memory, which should be available by 2018. Now you have this absolutely crazy chip that is going to have between 16,000 and 64,000 CPU cores on a single die, with 1 megabyte of memory stacked on top per core. So if you imagine now, it's a approximately 1 centimeter by 1 centimeter chip, and then you scale up. So it's about 8 dies, so about 4 millimeters high. So you get this 1 centimeter by 0.4 centimeter box that is has 16 gigabytes of memory and 16,000 CPU cores. And what are you going to do with that? That's the question. Because somebody should build this. It may or may not be us, because we're still a struggling startup company in 2014. But it's not a technical impossibility, right? It's not a science fiction. There's certainly going to be programming challenges along the way. There probably will be some tweaks to the network to allow us to scale to that. But we could take our little rectangle today, a little tile, and certainly scale it up to 16,000 cores. The power consumption, one really interesting thing is, if you do the power consumption right, if you're able to turn off all the cores, you can get to 0.2 watts standby power, which is very reasonable for an embedded device, and 20 watt peak, which is a little bit on the high side. But if we start thinking about 16,000 CPU cores in a 1 centimeter space in all kinds of embedded devices, what can we do? And this is clearly many thousands of orders of magnitude better than what we have today in current embedded devices, which means that what happens if embedded devices becomes thousands of times smarter than what they are today? For any size footprint, any size battery, what can we do with it? And I really, my goal now is to make that happen, by some way or another, because I want to see what people can build with it. So those are my slides, I'd love to hear what you guys think and what your thoughts are.
Q&A section now, so people can ask questions.
Yeah, absolutely. About anything, really.
So any questions?
Yeah. Why did you go on with the FPGA? Why not do a board without FPGA and drop the cost?
So first of all, we had to have a way to connect our chip to the host. So we said the board has to be able to run Linux, Ubuntu or Fedora or something like that, right? So there has to be an ARM or a MIPS or an Intel on there. And so we thought ARM has the best low power solution, most traction, so we should use an ARM. So, but then the question is, right, how could we connect to that ARM, right? There isn't really in an embedded world a coprocessor standard. So, and even if there was, probably our interface that we designed 3 years ago wouldn't be able to connect to it, because we didn't have a USB is too low bandwidth, right? I mean, you don't want to have a 100 gigaflop coprocessor sucking data through a 50 megabyte straw, right? It doesn't make any sense. So you need a high bandwidth, low latency interface, like you would have PCI Express, for example, in the desktop. But there's really no PCI Express for embedded, right? So really, there really was no. So we would have had to put something in there to do glue logic or something to connect our chip to any processor. And so, yeah, it really wasn't a good solution. And of course, with this Xilinx Zynq device, the really cool thing is that they have a dual core ARM, and then we hook up straight into that. So we sit inside the memory space like a coprocessor, like super high bandwidth, low latency, straight on the bus, kind of like on PCI Express. And so we could have reduced the cost, right? So let's say Xilinx Zynq in volume is $18 based on their public announcement. And we know that an SoC application processor, like a Broadcom or an Allwin or something, is less than 10. So we're losing $10 because we have an FPGA. So you go, all right, so if we're trying to compete with Raspberry Pi at the $25 to $35 level, that's a big deal, but we're really going after a completely different space. So we're going after the $100 to $150 space, where people, they want an FPGA, or they want our device, our coprocessor, more performance. They want this kind of unique platform. But it was a tough choice. I looked for a while. I looked at small microcontrollers from ST, and I looked at application processors like the Freescale, the OMAP. I couldn't find any way to connect it properly, our processor, to that.
Thunderbolt?
Well, Thunderbolt, I mean, then the question, it gets very expensive because we don't have a Thunderbolt interface on our chip. And then you go, right, so maybe we'll put an FPGA to convert the Thunderbolt to that, but it doesn't make sense, right? So then we have a 3-chip solution that's even more expensive than maybe the 2-chip solution. So, things get a lot easier when you move up to kind of a data center, right? So another thing we're working on right now is a PCI Express board. So there, you go, okay, PCI Express, people are used to paying more, right? Hundreds of dollars, if not thousands of dollars, if you talk to, about the big NVIDIA cards, and it gets a little easier. This space is, I mean, if you see, it's amazing how you look at the Raspberry Pi, the Banana Pi, the Odroid, the BeagleBone. How is anybody making any money, right? Raspberry Pi is making money because they're shipping millions. Anybody else, if you ship 10,000 units at $100, you're probably going to make $20 per board. And the guys who are selling for 45 might be making $5 to $10 a board. Now, let's say you ship 10,000 boards at $10 a board, you just made $100,000 in profit. But you had to produce a board, right? You had to design it. How many engineers did you put on it, right? If you put one engineer that did everything from procurement, from debug, from everything, right? And got the board to market and sold 10,000, you'd be out of money, right? You'd be done. So the economics are brutal because everybody's racing to zero. So nobody's making any money. So what I've seen happen is, both in the chip industry and in the board industry, is everybody drops their prices until people starve to death, and then there are less players and everybody goes out of business, and there's a few left standing, and then the volumes go up, they raise the prices, and then they can survive. But it's a very, very bad trend. And in the chip industry, same thing, right? So there were 10 companies looking to make smartphone processors, and so you have companies from China like Allwinner and Spreadtrum, and they make very cheap processors, like $5, $10, and they're dropping everybody's prices. So Broadcom, Freescale, and everybody else, they go, oh, if these guys are just killing the market, right? We can't compete with them on cost, and so everybody wants low cost, Allwinner, Spreadtrum, the guys are really high quality, right? The kind of Apple brands. So in the chip industry, it's Qualcomm, right? Qualcomm has, what is it, 60-70% market share in LTE, application processors. They're selling the chips for tens of dollars. So they're making a huge margin. They have the biggest market share, and now you have this kind of monopoly growing, right? And so you have a huge brand, Qualcomm, that is everywhere, and then you have the guys who are fighting for second and third, and they're, anybody comes in and drops the price, kills the market. They're the only ones left standing. Of course, they're also not making any money, because let's say you sell a chip for $4, and it costs $2 to produce. So you're making $2 per chip. Now you might sell $50 million, right, of chips, which is really hard, because when you look at the smartphone market, once you start fragmenting it, you realize that Samsung's not buying from you; they have their own chip. Apple's not buying from you; they have their own chip. So now you get down, and they're the big ones. Now you get down to tier 2, and tier 2 is like HTC and Motorola and a bunch of other Nokia and a bunch of other companies. They might be selling 50 million units, but there's 10 companies fighting for 50 million units. So you might have 30% of 50 million. So even to get to 15 million shipped is really, really hard. And 15 million shipped times $2 profit is 30 million. It probably cost you $30 million to build a chip, to engineer it with hundreds of engineers, the tape out, the IP, and everything else. So you end up breaking even. So it's terrible, terrible business. But still, if you look for a niche and you find your pocket, you can make something happen. I think the lesson here is, don't try to compete on cost, right? The people who compete on cost, there'll usually be one person standing. And in the case of the Raspberry Pi, they're standing. Everybody else is struggling.
Do you see parallel computing going into portable computers like smartphones and laptops in the future?
It's already there. If you look at the smartphone today, they all have GPUs that are OpenCL programmable. For example, you have the Mali from ARM. It's kind of a GPU for mobile. You can take a Chromebook, for example, and you can hack it and and unlock it, and then you can run OpenCL on it. And that's parallel computing. It's not the parallel. I hope that there will be more parallel computing, right? So you're always going to have a graphics processor on a consumer device because everybody wants good graphics. But there's nothing on it today that's tuned towards image processing, right? So things like automatic tracking, recognition, kind of the camera input. Everything is about displaying on the screen from a data file or generating something. So actually we went out and tried to pitch this Epiphany processor as an image coprocessor. And we went out and talked to everybody you can think of that's in that space. And the answer was more or less, come back to us when you have a complete solution with the software and everything around it. And we weren't going to do that because they didn't promise us that they would buy. They just said, go away and come back when you have it, which didn't seem like a good idea. But yeah, so there is parallel processing today. Certainly everybody has multi-core as well, right? They have quad-core, even octa-cores, and then they have the GPU. And maybe someday they will also have a image coprocessor. I know Qualcomm is working on a photography coprocessor. It's a very fancy image pipe. They can do things like image stitching, high dynamic range photography, programmable. Yeah, there is a lot. So what would be really cool is if these companies actually opened up their platform so you can access it. Because today, the standard is you go out and find your partners, right? If you're Samsung or HTC, you go out and find your partners and you say, all right, let's all sign NDAs, right? You can't share the data sheets, the user manuals on the web or anything like that, or SDKs. You can get an SDK, write a program, and then we license it from you. So you get this very closed ecosystem. And it would be nice if it was more like a PC market where pretty much everything's documented and anybody can do with the device what they want to do. You can load any operating system, any software. That is the future. I mean, because if you look at like a smartphone, right? I mean, there's the fact that people are selling smartphones for $100 today is incredible. The amount of power and connectivity you have in there. There's no point in making today a medical device, or generally not any point in making a medical device for doing something specific, because it's going to cost you $10,000 to build, like a GE ultrasound device. Better to connect a sensor to this very good device that you have today, a tablet or whatever it is. And so to leverage the economics of the high volume to get the cost down and just adding delta. But you can't add delta today because it's a closed box. You don't have any access to the documentation or any interfaces really. I mean, if you're lucky, you have a USB, right? If you're unlucky, you have an Apple that has their own proprietary interface. So it's I think the future of smartphones, I hope, is going to be that they'll open it up. Kind of like Google is trying to do now with the project called Aura, where they're trying to make a modular smartphone. It's kind of a science project, but actually the guys who make these phones, all they would have to do is publish their specs, and people can do something, and make it not illegal to hack the phone, right? So those two things would be good. So, so it's going to be parallel and hopefully more parallel.
Okay, you said that you have a solution for Linux operating system already portable to your system.
Oh yeah, Ubuntu 14.04.
It's just used.
Yeah, so.
Is there a solution available that you just install it?
Yeah, so what we do is we run everything off an SD card, right? So Basically, what you do is you plug this SD card into your regular laptop. You download an ISO image from the web, right? And then you do DD or disk copy to the SD card, eject it, and then put it in there, power up, and you're ready to go.
Let's face it, U-boot.
So the boot sequence is U-boot to Linux. So we run Linux 3.12, although just last week we actually got into there's a guy who runs an ARM server farm that what he does is nightly regression tests on the latest kernel, like today's kernel, right? The one that with the latest submit. So now we're running 3.17 dot whatever, right? So it's just kind of cool. So right now it's actually failing. We're failing the regression suite, so we're trying to fix that. But this happened like this week. So the idea is we want to join up with not be a fork or an offshoot. We want to be mainline. So we want to run mainline latest kernel, so we can do things like containers, right? So like things like Docker. So we can. I mean, that's great. And then same thing with protection and performance. So we'll get the latest, and then same thing with Ubuntu. Because we're running stock Linux kernel, we can run all the work that Linux has done. And they, of course, are just building stuff off the latest canonical Ubuntu 14.04. And so the whole thing is collaboration and leverage. So because we try to stay straight down the middle and then leverage as much as we can. Now the whole Linux Ubuntu U-boot story has been fantastic. I mean, whereas guys like TI 10 years ago, they were kind of paving the way on their own, breaking their teeth, spending tens of millions of dollars. We're just kind of grabbing things and doing make, compile, download, done, right? It's amazing.
What's the situation of parallel computing in critical systems like avionics and military? Do you know?
Yes.
So
the open story that people have talked about is NASA. So they bought a lot of boards from us, and they're working on a smart UAV project. So basically, the problem they're trying to solve is that right now everything is driven by communication link. So as long as they have a link to the UAV, everything's fine. But sometimes they lose the link for whatever reason, right? They're doing experiments near volcanoes and having interference and all kinds of things. So if they lose a communication link, the UAV is gone, right? So they need to put a system in there that will allow the UAV to gracefully recover or do something until they can regain the communication link. So that one started a month ago. Pretty big effort, a lot of engineering effort, a lot of boards bought. That's probably the most visible one we've seen. And same thing here, we have a pipeline. And then clearly there are a lot of commercial military vendors in the US as well. So we have every military branch, every government lab, every US prime contractor is looking at this. Not for the Parallella, but for the Epiphany chip, right? So they use this as an evaluation. They may or may not use this as a reference design. So the reason, one of the things that people like is the fact that you have a complete reference design. So when you design a board, you take a lot of risk, right? I mean, you have good board designers that you can usually do it right the first time, but you still have risk. What if you misunderstood how to connect a pin? What if you misread the data sheet? Something like this. Here, just say, all right, copy, paste. Take this, move it over here. Just go into the schematics, select these components, put them over there, right? It's much, much lower risk. And so the idea of having an open source reference design that they can just copy, now they can move much, much quicker. So they do like the openness, and they also like the Zinc. It's a good ARM-based device, open. A lot of these guys in those kinds of markets aren't buying in big volume. So they're buying 1,000 units, 10,000 units, and at those kinds of volumes, you can't get an all-winner device in the US. You can't get a MediaTek device or a Samsung device or even a Qualcomm device. You want to buy something off DigiKey, right? Where you go up and say, here, I'm just going to buy it. And there's only a few companies that sell things those kinds of low volumes. And Xilinx is one of them. So they like the openness of the architecture. Everything's documented. A lot of them like the FPGA, that they can actually go out and connect this to all kinds of sensors, gyroscopes, and accelerometers, and camera sensors, right? So, for example, one of the things we're also working on right now, we have a lot of parallel projects going on, but so you can connect a camera over USB, right? Which is not very high bandwidth. You certainly can't run uncompressed video at full frame rate. You could run gigabit Ethernet, the same thing, long latency. The cameras tend to be quite expensive, and instead of that, what you can do is you can take this backside cable interface and hook up a MIPI interface, like basically a consumer camera interface, a few lines of LVDS signaling, and you have a direct access, low latency camera at full resolution. Because there's 48 of those pins, you can have multiple cameras even, which you can't do over here, right? So people are pretty excited about that as well. In fact, there was a project that we didn't quite have enough pins for, but that was really cool out of Europe. They also did a Kickstarter campaign, or Indiegogo crowdfunding. They wanted to do a 4K cinema at 300 frames per second. So, like a Hollywood type camera, open source completely. They raised like 170,000 euro, and they're using the zinc for that. And so the idea was you put this 4K sensor, right? Here you go. Here's your camera, right? And a camera like that today would cost, I don't know, $20,000, and it's completely proprietary, right? So that was kind of a cool project as well. So we have a lot of people putting sensors, trying to connect them to the device, and for robotics, for drones, for machine vision production, that's kind of our sweet spot.
Yeah. Which languages are currently supported in parallel? I know you spoke about C, but are you aware of any other? Already.
So on the ARM, pretty much anything you can imagine. Right? So the ARM, Python, Java, Erlang, anything, right? Because it's just running Ubuntu. So anything you can do sudo apt-get install with, you can have. For the actual Epiphany, there's a lot of projects going on, but really the ones that are complete or usable, at least in this current form, is C and OpenCL. OpenMP is advanced, it's going to happen. Everything else is kind of experimental. Were any specific languages you were thinking about? Python? Also, Python's going to be tough on the Epiphany cores because there's only 32 kilobytes of memory per core. So you're not going to run a Python interpreter with it's just the wrong programming model for the Epiphany. It's the kind of thing that you would run on the ARM, right? So you run your Python program on the ARM, you maybe read some files, open a socket, do something like this. As soon as you get to the math, what you do is you do a Python call to a program that communicates with the Epiphany. So there's a guy, actually a guy here at USP named Lucas Teske. So he got a board, I met it down at Latinoware, and he did a Python plugin for our API functions. So that you can actually write everything in Python. So it's like a Python to C wrapper. And also it's up on the web, open source. Yeah, I guess you could say where you do Python.
It's possible to create a hypercube with the 64,000 cores connect?
Yeah, so I guess this. Yeah. So the short answer is yes, but you would have to build a custom system, right? So either by so what we found is let's say we want to hook up these two boards, one next to the other, right? So we can do that by either creating another board, a backplane board that these would plug into, or we can create cables, flex cables, that would have, a connector and a piece of flexible wire between them. But it would...
The idea is create a mesh.
Mm-hmm.
So big.
Yeah, and then, towards the edges, you can start wrapping around from both sides.
3 lanes only.
With
3 or 4 lanes
why 3 or 4?
of the mesh.
So actually, what we do, if you think of the array, right? So you have a 2D array, and then the sides would wrap around all of the sides, right? So it'd be all the links would go on one side, go to the other side, and then all the links on that side go to the other side, and that would make it complete. So there is a university in Sweden right now that's interested in that, and are looking into that.
It would be expensive to create and develop a hypercube for that.
It would, the development cost would be in making a custom cable, and we started doing a custom cable, and then realized that it wasn't a priority, right? So kind of, the question is always, do you develop something because you think people want it, or because a few people have said they want it, or do you develop it for a customer, right? I mean, the safe way is say, look, we have a customer, they already signed a check or a purchase order, we're going to deliver it. Because if we're going to keep developing products and putting them out there, right, we're taking a huge risk, and then we don't know if somebody's going to buy it, right? Maybe we'll only sell 1 cable or 5 cables. And so I think some of these things we're still looking for the right customer.
In this moment, can I use the parallel to launch parallel algorithms?
Yeah, so you would, the way you would usually do it, right? You would log into the machine, like you would log into a server with SSH, right? Now you're sitting at the ARM command line, your Linux. You can do anything you want, do PS for finding processes, write your C program, or compiler, or anything else. Now launching and I'll get into that after a short break to show you what it looks like. Now you start writing your C program, right? That's running on the ARM. And inside the C program, you do an include, right? Include for a library. You do include for a library to...
Open ACC,
something like that. But like in this case, until now, it's a little bit lower, right? So we've done our own API, which is memory mapped. So it has 3 calls: read, write, load program. And the way it works is the arguments the read and write looks like memcopy, right? You give a source address, destination address, and bytes to copy. And you give one more argument, which core you want to talk to. So let's say I have 16 cores. I say, all right, I want to talk to core 0. I want to talk to core 1, core 2, right? And all the arguments after that looks like memcopy.
So it is multiple instruction, multiple data.
Yes, it's MIMD, right? If that's what you meant, like multiple instruction, multiple data. Yeah. But the program that's running on the actual core is just a C program, right? That you've compiled with GCC. So you write a main routine, that does whatever it needs to do. You compile it. Now you have an L file, and in your host program, the one running on ARM, you would just read that L file from file system and load it.
So can I use that? I have to send the word for H1 parallel processors.
Yes, somebody has to. I should say not necessarily you.
For now.
Well, if you're running OpenCL, a lot of OpenCL takes care of that for you. But in terms of which core, you don't know which core you're talking to because there's a schedule that decides which core to send the thread to. But you still have to split up your data, right? You still have to do the ND range if you're writing OpenCL. So yes, the parallelism, somebody has to do it.